a senior research scientist at Google, New York. He completed his PhD at Carnegie Mellon, where he was advised by David Woodruff. He's interested in sketching and high-dimensional geometry. Most importantly, he's a Brown 2017 Math CS graduate, and he's going to tell us today about some new LSH stuff. So, with that,
I love how you're looking at me as if you're going to get something wrong. Is that right? Yeah. I couldn't remember what year I graduated. Thank you so much for having me here. It's surreal being back. I love this campus. I got to go on a little walk this morning. It's a beautiful day. But now I want to tell you something I'm also excited about, which is some new work we have on Earth mover distance. So the majority of this work is essentially on getting faster algorithms for nearest neighbor search, or information retrieval. We're looking at the ML application for this metric called Earth mover distance. And so this is sort of a problem I've been working on in various aspects for the last couple of years with Eric. He's at UPenn now. His student Tian just joined. So now we have a work together where we have some proofs and bounds here. So what I'll do, I'll start by telling you what Earth mover distance is if you haven't seen it before. So Earth mover distance, I like to think of this as like a meta metric. And the reason I say that is because it's a metric, a distance measure, over sets of points living in another metric space. So we have like some base metric space X. If it's helpful, just think of X as being d-dimensional Euclidean space for the rest of the talk. And we have two sets of points, A and B, which are subsets of X. And Earth mover distance is a metric over such subsets. And let me just mention now that for the rest of the talk, all these sets will have the same size. They'll be fixed to have the same size S. This is not a requirement. Like everything I say here, there's a very easy way to generalize this. I won't mention it because it's not really necessary, but these sets can have different sizes. But for now, let's just have them all be the same size S. So what is the Earth mover distance? Well, it's the cost of a minimum, that's the minimum cost of a perfect bipartite matching between the points in A and the points in B. Well, where the cost of moving a point from A to B is the distances from the underlying metric space. So it's the minimum over all bijections from the points in A and the points to B. If I think of it as a matching, I'm trying to match up the A points and the B points. And then you sum the cost of each A point with its matched B point. And the Earth mover distance is the minimum such cost over all matchings. So you have your triangles and your stars. This is making me want to look over here. Usually, and you want to find the best matching between the triangles and stars. And the cost of the Earth mover distance. So this seems like sort of a complicated object. Why do we want to make things more confusing as distance between the pair of points? Well, it turns out there's a lot of applications where using distances over sets of vectors gives you much better quality. And one of the canonical applications comes from natural language processing. This is something we think about all the time now. And I'm going to call this sort of a classic application of Earth mover distance. Classic because this is from ICML 2015, which is now 8 years old, 9 years old almost. And this is from the paper of Kusner, Sung-Polka, and Weinberg. And what they use is this as a way of determining similarity between documents. So in the very classic world of NLP, you could look at these two sentences, Obama speaks to the president of Chicago, and in Illinois, the president's free with the media, as like a bag of words. And bag of words models would tell you, hey, these sentences have absolutely no words in common, they're very dissimilar. But of course, we know that these sentences are describing very similar actions. And in fact, you can sort of do a semantic matching between the words in these sentences, where Obama was the president at the time of the paper, Chicago is in Illinois, the press is like the media. So there's a semantic matching between these words. And we like to transform that into a metric space problem. And the way we can do that is through the magic of embeddings. So at the time, you would use an embedding like word2vec or glove, which takes every word in the sentence and transforms it into, let's say, a 128-dimensional vector, a vector in Euclidean space. And now each of these sentences or documents is just a collection of vectors in Euclidean space. And you can use Earth mover distance as a measure of similarity between these collections to measure semantic similarity between the documents. And so this is what that paper, the word mover distance paper, was about. And you can see that the magic of embeddings is that similar words map to similar points. Illinois maps to a vector similar to Chicago. Press maps to a vector similar to media. And so the Earth mover distance being small indicates that the sentences have similar meaning. So that was a classic application that inspired a lot of work. What I'll say now is that there's sort of a more modern take on this embedding approach. And these are so-called contextualized embeddings. So the only difference here is that what we do now is instead of embedding each word independently, we send the entire document through a self-attention model. And all that means from a theory perspective is that the embedding of every single word is going to depend on all the other words it came with. It depends on the entire context. So it's like a data-dependent embedding. So this sentence, the byte race past the something or other, every word gets embedded into a high-dimensional vector, but the quality is much higher now because the embedding of byte depends on the entire context that it was in. And the only reason I bring this up is, and this is the majority theory talk, we're just talking about like some applications I'm very excited about, is because it's actually using this as a method for information retrieval and for document similarity is the state-of-the-art method in terms of quality for like all the biggest benchmarks, in particular this Bear benchmark for information retrieval. If you use these sets of embeddings and use the similarity between the sets of embeddings, this is how you get state-of-the-art on these benchmarks right now. And there's a whole suite of models. These models are just about producing multiple embeddings per document to get higher quality. So there's a huge quality gain to be obtained by looking at sets of embeddings instead of an individual embedding.
But D has gone way up here.
D has gone up. Well,
are you gonna? But maybe you can.
So it not only has D gone up, but the similarities become more complex. It's no longer a
Euclidean or something.
And so this is the problem. And what we usually want to do with these things is retrieval. So we usually want to solve the information retrieval problem. And the goal of my talk today is to tell you some techniques that solve it more efficiently, even when our metric is more complicated. And at Google, one of the main things I do is work on systems that hopefully make this more efficient in practice as well. Maybe for a slightly simpler metric on sets of points. But what is the information retrieval?
Just before we leave the practical side, so are there products now that use something like this?
Not at Google scale. The hope is that yes, soon. But there's a lot of efficient. All those papers. This is like really active area research. But these are all at most like 3 years old. So there's recent work trying to get this to work, and we have a huge scaling issue because we want to get these algorithms to be as efficient or nearly as efficient as the algorithms that do information retrieval by a single vector. Because we have 25 years of research of doing information retrieval and nearest neighbor search for single vectors, and like 2 years of research on doing it for sets of vectors. And so I think the answer will be soon. And that's my main goal is to get that to happen. And it aligns with a lot of my theory research stuff. I'm hoping that happens, but not yet. At least not that I'm aware of. So the problem that we can think about is this information retrieval problem. I have a document data set. Each document is like, let's say, a Wikipedia article. And then I get a query. I'm allowed to, let's say, pre-process it, not to spend some time processing it. And then given a query phrase Q, like when was Abraham Lincoln born, I want to very quickly find the most relevant document. So here it would be the Abraham Lincoln Wikipedia page. And the important point is that I want to find this document much faster than a linear scan. I don't want to compare my query to every single document, compute a similarity, and find the most similar one. That would be way too expensive. I want to be able to compute this way faster than a linear scan, like in sublinear the size of the data set time. And so in theory, this is called the nearest neighbor search problem. And this also has like a 3-decade history of study. And there's a lot of beautiful results in this literature. And so what is the theoretical framework? Well, so I have some metric space X. This is going to be like where my documents live. And I have a data set subset of X, of n points. And I'm going to have some approximation factor C, which is larger than 1. And my goal is to pre-process the data set such that given a query point that also lives in my metric space, I quickly return a C approximate nearest neighbor. What is a C approximate nearest neighbor? Well, it's any point whose distance from my query Q is within a C factor of the nearest distance in that data set D. And so the picture here, I have my query Q. Y is the nearest neighbor at distance 1, but I'm allowed to return a point in the bigger annulus of C factor larger. And so briefly, it's important to note that for this talk, we're interested in nearest neighbor search where the metric is earth mover distance. And remember the earth mover distance, just to remember the picture, it's a metric over sets of points. So here your data set actually consists, one data set point is actually a subset of S points in your metric. So one data set point could be these squares, of which there's 4 points in the metric space. And the query is also multiple points of size S in the metric space. And you want to find the nearest set, which is a point in earth mover distance. So it's important just to keep in mind, because it can be confusing for obvious reasons, that a point in earth mover distance is a set of S points in my original space. So this is the picture for earth mover distance. So before we go any further, some boring housekeeping. I want to give a name to this metric space, earth mover distance. So I'm going to say EMDS with, in parentheses, the base metric. That's going to be my notation for the earth mover distance metric space, consisting of sets of size S in my metric space X, with the earth mover distance as the metric. And for the rest of the talk, this base metric is going to be d-dimensional space with the L1 distance. The reason we're going to use L1 instead of L2 is because it's more general than L2. We can embed L2 into L1. We can embed a lot of other norms into L1. Maybe we lose something in terms of getting better results, but for simplicity, we can, like the most general setting for these sorts of results will be L1. And I'm just going to assume all my distances are between 0 and some delta, just to have some bound, and we can assume that the dimension is some polynomial in S. There's some simple reductions. So just our notation, D is our input data set, N is the size of our data set, the number of points, and S is the size of a single subset in the EMD metric. And so you can think of N being much larger than S, because N is like the size of the data set, the number of Wikipedia articles. S is just the description size of a single document. So what are the kinds of things that we could hope for nearest neighbor search? So this is a classic result of Indig and Matwani from Stock 98, and they proved a result which I'm going to call the gold standard result. And they proved nearest neighbor search algorithm for the L1 distance. So a single vector finds the nearest neighbor in L1. And this is sort of what I want to think about for the rest of the talk is like the goal we could dream of. So their data structure has the following properties. You get to specify a parameter epsilon, and then the approximation, think about epsilon as between big small. The approximation is like 1 over epsilon. So you can think of epsilon as being a small constant. The space and preprocessing time is nearly linear in the number of documents, n to the 1 plus epsilon. And the query time is very sublinear, it's n to the epsilon. So it's much faster than doing a linear scan through all the documents. You can, I think for the rest of the talk, the important trade-off here is between the query time and the approximation. The space and preprocessing will almost always be n times the query time. So let's just think of, really the trade-off we're looking for is like a 1 over epsilon approximation, n to the epsilon query time. That would be great. And this is also gold standard for the second reason because it's actually optimal. And we know, Eric had a paper with some of his collaborators showing that under, sort of broad strokes computational model, you can't really do better than this for LSH, for nearest neighbor search for the L1 distance. So we really can't hope to get much better trade-offs than this. We get slightly better for L2, but this is really, by and large, the trade-off you can hope to get. But now I want to say something about this term in the title of the talk and also the technique that was used for almost all of nearest neighbor search results in high dimensional space, that is. And this technique is called locality sensitive hashing. And if you haven't seen this before, it's a really nice idea that I think is actually quite elegant and beautiful because it can resolve a lot of geometric problems. And an LSH, it's a hash function, but it's not a random hash function. It's a hash function that respects the geometry of the metric space. So it's going to be a hash function that has the property that points that are closer together in the metric space are more likely to collide. So formalizing actually isn't that much work. So here's a formalization. If I give you an epsilon, you get to choose epsilon, and a threshold r, think about r as a distance in the metric space, then I'm going to define an epsilon r c times r LSH family. This is c is the approximation. Is a hash function that has the following two properties. First, you want to have a close points colliding property. So for any 2 points x and y in my metric space, if they're close, if their distance is less than r, they should collide with large probability. Let's say probability at least 1 minus epsilon. On the other hand, points that are far should be less likely to collide. Let's say if their distance is larger than c times r, they should collide with probability at most 1/10. So far points are unlikely to collide, close points are likely to collide. And close and far are split by this approximation factor c. Okay, so how could we use this? Well, let's look at an example. What if I set epsilon to be like 1 over 100 log n? Remember, n is my data set size. And I'm going to use this hash function g of x, which is a k-wise concatenation of my LSH. So that in k is like, let's say 10 log n. So what that means is that to collide under g, you have to collide under all the h's. So this has the effect of raising these collision probabilities to the kth power. So if I did this, well, what happens if I raise 1 minus epsilon and 1 to the kth power, where k is 10 log n and epsilon is 1 over 100 log n? Well, a simple computation shows that the probability that close points collide is still fairly high, it's at least 2/3. But now the probability that two far points collide is like 1/10 to like the log n. So that's like, some large polynomial in n. It's like 1 over n squared. So the probability that two far points collide is now very small. And in fact, because there's only n points, you can union bound over them never colliding. So you're never actually going to collide with a far point under this parameterization. And now, how can I use this for nearest neighbor search? Well, the algorithm just sort of pops out here. I can just take one of these hash functions, g, and hash all my points with g when I'm pre-processing. That's just one hash function. And then when I get the query, I just hash the query. I look at the bucket. It lands in constant time. And I return any point it collided with. And I know that I'll never collide with a far point. And if there was a close point, I would collide with it with constant probability. So I'm in great shape. This is an algorithm for nearest neighbor search that runs in constant query time. And then maybe you have to repeat this for different scale, for log n scales. But so this actually is a bona fide algorithm. If I handed you such a hash function, you need such a hash function that has these properties. It turns out in general, there's a general reduction. If I gave you an epsilon r c times r LSH function with these parameters epsilon and c, then you can get an algorithm for nearest neighbor search that runs an n to the epsilon time and has a c approximation. So this is a simple reduction, and the takeaway here is that we might as well focus on locality-sensitive hashing. This is the main tool that's being used for these kinds of problems, and it's also will immediately give you nearest neighbor search. Let's try to get the best LSH functions we can. So we already saw some results for L1, but what about Earth mover distance? Well, there's like 20 years of research plus on this now, and so like we have really good understanding of LSH for things like L1, Hamming distance, Jacquard distance, all the very common metrics. But we don't have good LSH functions, for some definition of good, for EMD. And one of I think the obvious reasons for this is that Earth mover distance is not a simple metric, in the sense that like most metrics like L1, L2, they decompose nicely into a sum of distances across coordinates. But Earth mover distance doesn't decompose into some arithmetic sum. In fact, it's some complicated matching process. And in fact, if you wanted to solve it more than let's say 20 years ago you wanted to solve it, you'd probably use a Hungarian algorithm, which has over 100-year history. It dates back to Jacobi in the 1850s. And this algorithm computes augmenting paths and takes n cubed time. Now, the fastest algorithm, you could run these really fast recent min-cost flow solvers that run in nearly quadratic time. But even those are quite complicated, and there's actually conditional lower bounds saying that it's probably unlikely to do better than n squared time. So this isn't important for the talk. The takeaway here is that this is a computationally complex metric, and there's no simple way to describe the optimal solution to it.
But these are exact algorithms.
These are exact algorithms.
You're okay with them?
I'm okay with approximations. But one interesting thing is the second you want to dip below this n squared, now you need to use the only way we know how to do that is to use LSH somehow. But yeah, this is one reason why there aren't simple space partitions for EMD. But there are space partitions, and we'll just know. But this is sort of the reason why we don't have algorithms that are as efficient as for LP norms. But we do have algorithms. So what are some of the things that are known? Well, Piotr in Stock 04 had, I think, what I'll call the first result on nearest neighbor search for this. The paper wasn't about nearest neighbor search, but it implies this result. And what did we get? Well, he was able to show a data structure for EMD with S points that has something that looks kind of like the ideal trade-off, but it has this extra factor here. So the approximation, instead of just being 1 over epsilon, it's 1 over epsilon times d log s, where d is the dimension and s is the number of points. So this is an ideal if the dimension is large, because we're getting the approximation is growing with the dimension. And so this was approved slightly later by Andoni, Indick, and Kraftgammer in SOTA 2008. And what they showed was essentially you can replace one of the factors of d with a log s factor. So if t is larger than log s, then you're getting an improvement. So log squared s approximation instead of a d log s. And the main result I want to tell you about in this talk is a further improvement it's going to be in stock this year. We shaved one of the log factors basically. So instead of having a log squared s approximation, we get it down to a log s approximation times some polylog terms, polylog terms
In
S. Yeah.
So all three of these is exclusively EMT?
Yeah, it's all about EMD. Yeah.
They don't generalize to other...
Well, okay. So these actually both give you algorithms for MST as well. It'll become clear how they give tree embeddings. So they're doing the tree embeddings of space with better approximations. And so if you have another computational problem that's easier in a tree, then this will give you a better algorithm for that by routing it into a tree.
Whereas yours is really specific.
Ours, Yes and no. I'll say something about that. I think it'll actually be it'll be easy to see what part of our algorithm is specific. But at the end of the day, I think the new result is mostly specific to EMD. But a lot of these works give very general techniques for high dimensional space.
Sorry, the query time. I remember it was constant before.
The n to the epsilon. Oh, so in that one slide I was giving an example. So if you set epsilon to be 1 over log n, then the n to the 1 over log n is a constant. So if you could set n to the epsilon to be 1 over log n, then you would get a log n approximation here, but you get constant query time, and that's a valid setting. Yeah, like you're allowed to pick epsilon here. Okay, so like I said, these papers actually didn't talk about nearest neighbor search. They were really sort of focused. They weren't even really focused on LSH, but they proved something more similar to this, which is they proved the existence of certain space partitions, or let's say localities of the hash functions. So they proved the existence of LSH families under the definitions that I wrote down earlier, with the parameterization epsilon r d log s and log squared s. And by the reductions I told you, that these gave the result in the prior slide. So these papers gave localities of hash families for Earth orbit distance. And the main result I want to tell you about today, phrased in this language, is a new tilde log s approximate data-dependent locality-sensitive hash family. So I haven't told you what that is yet, but you can sort of see here that like we're playing a slightly different game than these two papers. These two papers gave hash families that were data-independent. We're going to play a slightly different game and give a data-dependent hash family.
In your original framework, you started with one hash function and then you kind of assumed that there would be multiple independent hash functions.
Yeah, you have to be able to draw them randomly from the family. Like the definition is a definition of a collection of hash functions, and the probabilities were oversampling a random hash function from that family. So under the definition, it's like I have a hash family, which is a potentially infinite set of hash functions h, and I'm going to draw a hash function randomly. The probability is over the random draw of hash function.
Okay, so the hash functions don't have to be independent.
For this, you would want them to be independent. Yeah.
So you have to prove that.
Well, I have like some description of the hash family that I can easily generate random draws from it. So I mean, in general, like the hash family is usually very simple to describe. It takes a small number of random bits, so I can just regenerate the random bits and get a new hash function.
Okay.
I'll show you such a hash function in a moment. It should be hopefully clear that you can easily generate a new one from scratch. So let me tell you what a data-dependent LSH is actually. So it's a very similar object, but there's going to be two changes. One of them is that the hash function that I draw, the hash family, is going to be allowed to depend on some input data set D. So I have a data set first fixed, and then I generate the hash family. Now the first condition is exactly the same. For any 2 points in the entire metric space, not just the data set, they should collide if they're close. But now I'm going to have a weaker property for the far points. I'm going to have the property that for any point x in my metric space, I only need to split from far points in the data set on average. So I have my point x, which is any point in the metric space. And the guarantee is that only over a random draw of z from my data set, conditioned on z being a far point, so you draw a random far point from a data set, only over that draw do I need to split with good probability. It's a weaker statement.
But when you sample the hash function, does it also depend on the data set?
Yes. I mean, so it need not depend, but it's allowed to depend, right? Like you could satisfy this condition. So a data independent LSH also satisfies this condition. It's stronger, so it doesn't have to depend on it, but it's allowed. Now you're allowed to depend, and ours will depend on it. It's like if you satisfy this, but you don't satisfy it for all points, you can imagine that your hash family probably depends on the data set. Okay, good. So, so this is what we're going to hope to get. And before I jump into any technical details, what I want to do is sort of give a bird's eye view of how this result comes about and the game plan for the rest of the talk. So what we're going to do is I'm going to do maybe one more bait and switch. What all these papers really talk about and what the main technical result is actually the existence of something called a probabilistic tree embedding. And this object of tree embeddings is the object which is used to get the LSHs. So a tree embedding is just an embedding of d-dimensional space into a tree metric, which is a much simpler metric, that has nice properties on the distortion of the embedding. And these properties are the properties that you need where you get the approximations. So under this language, this paper of Andoni, Indig, and Kraftgamer, what they actually did was show the existence of a log squared s approximate tree embedding, embedding of EMD into a tree metric that had a log squared s approximation. So actually, with some of my collaborators, Eric Weingart and Shi Chen and Amit Levy and Stock 22, we tried to improve this result. And what we did was we showed that there's actually a better tree embedding that's data dependent. It depends on some data set omega d, and embeds d into a tree with a better approximation, potentially better, which is log of the size of the data set. So if your data set only has s points, you get a log s instead of log squared s approximation. So this is sort of the starting point of this work. So what do we want to hopefully get a log s approximation for nearest neighbor search, but we can't run this on the entire data set because d has endpoints in it. So now our approximation would depend on n. So what we're going to do is, if we want a log s approximation, well, we can start by sampling s points from the data set. I'm allowed to do that. So we're going to sample a random sample of my data set of poly s points, and I'm going to think of them as the original points. And so now I can run the tree embedding from this on those points. That gives me an embedding from the sample to this tree. I haven't described how that works yet, but I'll formalize this in a moment. That gets a log s approximation. That's what I was hoping for. And now sort of the key technical step is that what we're going to want to do is extend this approximation from the sample to points around the sample. So in particular, we're going to have this extension lemma that shows that I can now give a mapping from all the points to a tree with the property that points that are close to my sample, under some definition of close, they inherit the good approximation guarantee. So if they're, let's say, what I'm going to say, a log 10s neighborhood of my sample, they'll inherit the improved approximation. And then I now have this issue that I need to deal with the far points, the points that weren't close to my sample. And for that, we're going to use this earlier approximation. So this is a worse approximation than log s, but it's enough to distinguish distance r from distance r times log 10s. So this is where we can use this to split off the points that are far from a sample. And then finally, we'll glue these things together so that the close points are handled using this data-dependent approach. The far points from the sample are handled using this earlier approach. And that will be enough to get our final picture. So this is where we're going to go.
Wait, so that's an algorithm for the search. That's not an algorithm for LSH.
Yeah, so there's going to have to be some way to glue these two LSHs together. So
I see.
we're going to have one LSH here. So both of these are tree embeddings into a tree. I'll give you 2 slides. Yeah, actually, next slide, one after this one. So I'll tell you what a probabilistic tree embedding is, and then I'll tell you why, if you have one, you have an LSH. So what is a probabilistic tree embedding? Well, like I said, EMD is not a simple metric. So usually what we want to do is embed EMD into a simpler metric, and this is, of course, used all over computer science. A classic simple metric is a tree metric. And what I'll tell you is the following fact, is that earth mover distance, if the base metric was a tree, is actually a simple metric. And so what do I mean by that? I mean, you have a tree with distances over the distances of the shortest path distance on the edges, and your points are vertices in the tree. And so you have some red points and blue points, and I want to look at earth mover distance of matching the red points and blue points in the tree. Why is this a simple metric? Well, it's a fun and fairly simple exercise to show that the optimal matching in this case is just a greedy matching. So if I just move the points up greedily and greedily match any points that land in the same node, I'm finding the nearest neighbor and just greedily matching points to the closest point, and arbitrarily and greedily matching them. This is an optimal matching in a tree. It's fairly easy to show that. And because of this fact that greedy is optimal in a tree, there's a very nice secondary fact, and that's that earth mover distance over a tree embeds isometrically into the L1 metric. And so what that means is if I have a set of vertices in a tree, and I can embed that set of vertices into a single vector with the property that the distance between two embeddings of single vectors in L1 is exactly equal to the earth mover distance between those points. Which means that, from like embedding language, this means that earth mover distance over a tree is the same, is contained in L1. It might as well be L1 distance. And we know L1 has good nearest neighbor search data structures, so we have good hash functions for L1. So we can just use the nearest neighbor search hash functions for L1 to get our approximation. So if I have a tree embedding, it ends up giving me an embedding into L1, and then I can just use my hash functions for L1. So a tree embedding immediately gives me a hash function.
And sorry, what's the value of K?
Good question. So potentially infinite, but the important thing to note is that when you actually use it for nearest neighbor search, the hash function only needs to inspect a small number of coordinates of the vector, and practically you can make it. So it's large, it's exponential indeed, but it's going to be sparse. Like any vector is only going to have like s times log n non-zero coordinates. Yeah. The embedding is also quite nice. Like I would tell you about it, but I want to tell you about other things instead. And it's a simple embedding into the tree. So it's not that complicated. Yeah.
Is it a hierarchically separated tree? Or is it an arbitrary?
The tree will be HSD. Yeah. Yeah. But this is true for any tree. The fact that you can embed Earth mover distance over a tree into L1 is true for any. It doesn't need to have geometrically increasing edge weights. So our goal is going to be to get into a tree. How can we embed high dimensional space RD into a tree metric with small distortion? So that's going to be what we're talking about for the rest of the talk. And the first method of doing this, I'm going to call this the quad tree method. This was what I'm going to attribute to Andoni, Indick, and Krauthammer. Quad tree refers to something earlier. This is a slight misnomer, but I'm going to call it the quad tree for now anyway. So what is this method? Well, it's actually a fairly simple way of taking high dimensional space and embedding it into a tree. So what we're going to do is I'm going to look at my entire space, and I'm going to recursively split it up. Every time I split it, I can think of having a recursion tree, where the vertices of this recursion tree, the root is the entire space, and then the children are the two separate spaces that I split it up to, and then I recursively split it further and further and further. And then you could think of a point P in the original space as tracing a path as you go from the root, the original space, into the parts that it was subdivided into. And eventually it ends up in a leaf where that leaf corresponded to just that single point if I subdivide it, infinitely far, or if I discretize. And so now I have a way of creating a recursion tree by recursively dividing space, and I'm going to define edge weights of this recursion tree such that I have the hopeful property that the distances in the tree correspond roughly to distances in the original space. That's my goal. And it's going to be an HSD, a hierarchically well-separated tree, which means that what that means is that the edge weights are going to be geometrically increasing as you go up the tree or decreasing as you go down the tree. So for practical purposes, that means that if you just care about, let's say, roughly what the distance is, what matters is the first point in the tree where you split. That's going to dominate the distance. So the picture is like this. I have my points. Let's say I'm in the plane, and I'm going to make a random cut, splitting them in half until like the left side and the right side. And then I'm going to make another random cut and another random cut, and I'm going to keep splitting up space randomly and recursively until every point is in its own leaf node. And now I have my embedding. This point goes to that thing. This point goes to that one down there. I should have labeled them so it's clear, but maybe that would have been too many labels. Yeah.
I guess the way you've drawn the recursive random cuts, you're sharing randomness between the first.
Yeah, it turns out it doesn't matter. You can do it like a lot of these arguments. The arguments you'll need here will be an expectation, so it's okay. It's okay if they're not random intended. Okay, so slightly more detail. What do you actually do? Well, you impose a random grid over our d-dimensional space, and just a grid, and then I'm going to randomly shift it once. And that grid, I'm going to do it recursively with different side lengths. So the first side length will have all the points in it. Then I'll cut the side length in half, and then forth and so on. And then this is how I recursively partition space. And so I'm going to let T be the recursion tree. Remember, a vertex in that tree corresponds to a sub-hypercube of the space. So I'm going to write S subscript V to be the definition of that subset of space. And now I'm going to fix an edge weight for every edge in this recursion tree. So the weight between two edges U and V will be some value. I want to emphasize it's not important what this value is for the talk. What is important is it's some fixed value that only depends on the depth of the edge of the tree. It's like D over 2 to the I. Or D times delta over the aspect ratio over 2 to the I. So you don't need to remember what the edge weight is, but what's important is that it's some fixed value. In particular, it doesn't depend on the data that you're actually trying to embed into the tree, at least not for now. And then this is going to give us an embedding from d-dimensional space into a tree just by mapping a point A to the leaf vertex that it goes down to all the way at the end. And this induces a mapping from Earth mover distance over d-dimensional space to Earth mover distance over trees in a natural way. Simply, if I have a set of points in d-dimensional space, I map each one of them. Now I have a set of S points in a tree. So now I can look at Earth mover distance in the tree. So now we have a way of moving to Earth mover distance over a tree. Remember, this was our goal. So now we have to ask, what is the distortion of this embedding? Go
You
ahead.
said it wasn't data dependent, but don't you have to keep going until there's only one
So
point
you can
in
think
each?
about discretizing the space. So like in a computer, these things are going to be each coordinate is stored with log delta bits, let's say. And so after like log d times delta recursive subdivisions, there's only 1 point remaining in a grid cell. Because if I down to the precision I have, there would only be 1 point left. Yeah, after like logarithmic many split cuts. So what did Andonian and Krauthammer show about this mapping? Well, they heard, first of all, the distances of the tree are non-contracting with large probability. So the distances in the tree are always at least as large as the original distance with high probability in S. S is the size of the set. They also show the following thing, that the expected expansion of distances is bounded. So in expectation of the random draw of the quadtree, the distance between points in the tree only grows by a log squared S factor from the original distance. So these two facts, it turns out, are enough to embed EMD. This is for a single point. Why is it enough? Well, first of all, expected expansion is enough because you actually only need to show that one set of distances doesn't expand by very much. In fact, the optimal one. So the optimal alignment doesn't expand by more than log squared S. For every other way to match them up, you need to show that it doesn't shrink by too much. And for that, you can union bound over all S squared distances between the points in A and the points in B for the contraction statement. And then this is enough to give you the distortion between one set of points, and EMD gives you a log squared S approximation. So this shows there's a metric embedding for EMD over d-dimensional space to EMD over trees with a log squared S approximation. Good. So one thing I didn't mention earlier that there is a whole literature on tree embeddings from like Bartal and FRT from like 20. There's an important point about these tree embeddings that they're very efficient to compute. Given a point, I can very quickly figure out where it goes into the data set, into the tree. And that's going to be important for these things. So even though the results like this for betting into trees have been known, much earlier they weren't known by fast algorithms. If you weren't aware of those in literature, it doesn't matter. But if you were aware of it, this is my defense. So let me now tell you about the second tree embedding that I talked about. And this is going to be what I call the data-dependent quadtree embedding. And you can already sort of guess roughly what I'm going to do. I'm now going to allow the weights of the tree, the edge weights, to depend on the data set that I'm embedding. So importantly, I'm going to generate the exact same recursion tree. The vertices of the tree are unchanged. So they correspond to the exact same partitions of space. But now I'm going to fix some data set omega, and my embedding is only going to be defined on points in that set omega from RD. And the way I'm going to define the edge weights is I'm going to look at an edge, U and V. These are two vertices in the tree, so they correspond to two partitions of space. One, the parent, which has a large partition of space, and then V is the child that has some subset of that. And the way I'm going to define the edge weight is I'm going to sample a random point from my set omega that went through the parent, that lived in the parent set, sample a random one that lived in the child, and look at their distance and expectation. So what this is giving me is instead of having a fixed edge weight, it's giving me an edge weight that more accurately represents the distances between the point set that I actually have. So it's going to give me a more accurate representation. And so the picture is I have some vertex U, which corresponds to some large subset of the space, and it has a bunch of points. And then I have the child V, which is a subset of that. I sample a random point from each of them, and I look at the distance and expectation over that sample. And that's my data-dependent distance. So
okay, so just because U and V are nodes of your tree.
Yes.
They're parts of the space partition.
Exactly.
And X and Y are original.
Yes, exactly. Yeah. And I'm trying to define the tree metric. So to do that, I need to define the distances in the like edge weights in the tree. Yeah. And so the main message of the stock paper from a couple of years ago was that we showed that you can actually get an improved approximation using these data-dependent weights. So just with this change alone, and I'm not hiding anything in the algorithm here. This is the whole algorithm. Although the analysis was slightly painful. But we were able to show that for any set omega, if you use this data-dependent quadtree analysis, you get no contraction. So there's actually a nice triangle inequality argument to say that for 2 points in my sample, I never contract, and my expansion is almost a log omega factor larger. So if omega is like only size S, I get a better approximation. One thing I want to mention, though,
is that tight?
Well, it's tight for high dimensionally put in space. So we know that like Bartal trees, like log n approximation for arbitrary metric is tight. And it's also tight for high dimensional Euclidean space. So for like, if D is large enough, you cannot embed a subset of endpoints in RD to a tree metric with less than a log n approximation. That's known to be tight.
Yeah. So you're also
this is
a log factor.
Yes. Yeah.
Log, poly log.
Just one, actually.
One. Okay.
Actually, there is 2 in the original paper, but I think we can. There's a simple way to get one. But I don't know how to get rid of the last one yet. But one thing to note is that, look, at these conditions are only for points in the sample. And note that I only defined edge weights for points in the sample. If a sample didn't go down one of these edges, then this is an undefined value because there's nothing to sample from those sets. So this is only defined for points in my sample. So if I set omega to be the union of 2 sets of points in EMD, A and B, now there's only S points, and I get a log S approximation. And so the point of that earlier paper was that this would give you like streaming algorithms and things where I only have 2 sets and I'm trying to estimate them in some sublinear regime. But as I sort of hinted at earlier at the beginning of the talk, this isn't going to give us improved nearest neighbor search because we'd have to set omega to be the entire data set, and that has endpoints. And so it's improved if n isn't too large, but remember I'm thinking of n as being the size of the input, and s is the size of the description of a single data point. So log s is much better than log n. So we're going to try to avoid that. And the way we're going to avoid that is by using this so-called sample tree. And now we're going to get to this idea of how we're going to glue all these things together and get an improved bound. So what is the key idea? It's actually, it's a very simple idea. So I want to try to use this prior data-dependent tree embedding to get the better approximation, but I can only afford to use it on a small number of points, only polynomial and S points. So what I'm going to do is I'm just going to randomly sample a set omega for my data set of poly S points. Remember, a point in the data set consists of S points in the original space. So if I expand it out, I end up with polynomial and S points in the original D-dimensional space. And then what I'm going to do is I'm going to define the same exact quadrant. It's the same vertices as always, the same partition of space. The only thing I'm going to do is I'm going to change the edge weights again to be so-called like hybrid weights. And what I mean by that is I'm going to look at the edge that I care about. If a sample went down that edge, at least one, then I'm now able to define the data-dependent edge weight. So it's going to be exactly the data-dependent edge weight. If no sample went down it, well, there's no way to define an edge weight. Well, what am I going to do? I'll do the natural thing. I'll define it to be the fixed edge weight that was done in the prior data-independent work. Just the maximum distance divided by 2 to the depth of the edge. So this is the data-independent edge weight that was used in the Andrew and Kraftian paper. So this is, just a very natural way to extend the defining edge weights for points which were not in my sample.
Sorry, why do you need to do that? Aren't you only going to use these
No, it's
of
just
the
a
sample
sample.
points?
Well, I want to use it on the entire data set.
I see.
And in fact, for nearest neighbor search, this is a problem I glossed over. I want to use it on my query, and my query wasn't in my data set. So this has to be defined on points that weren't even in my data set, let alone points that weren't in the sample of the data set. So it needs to be defined on all points. But now it's defined for all points. It's a bona fide embedding of RD into a tree metric. And so, so it's actually a valid mapping of all points in RD to a tree metric. So the picture is like this. If these orange points were my sample, and I have some point A, and I want to look at its distance to, let's say, this other sample x3, well, I have to go up these edges, these blue dotted edges. They don't have any sample in them. So the first set of edges, W1, W2, they'll have the data independent weights. But at some point, I'm going to reach the path where I ran into a sample, and now the remaining weights will be data dependent. You can kind of think of these as being sort of the bad edges and these being the good edges. I want to have as few bad edges as possible because those are the ones that give me the worst log squared S approximation, very roughly. So let's look at the distortion. So what is the distortion of this thing? Well, let me now state maybe what's a trivial fact. If I have 2 points in my sample omega, what is their distortion? Well, it's log S because their distance in the tree is exactly the distance that they had in the prior data dependent work, so they inherit the same bound with no new work because they're only using the data dependent edge weights. But now the interesting question is, what can we say about points in my set that distances that were not points in the sample? Well, first of all, if 2 points were not in the sample, and moreover, if they were really far away from any point in the sample, then you can imagine that their path in the tree to each other would only use data-independent weights that didn't have any samples in them. And so their distance might as well have been the original distance from the earlier Andonian and Krautkamp paper. So these points are going to get a log squared S approximation. So already we know that this construction is not going to be enough because far points are not going to get a good approximation. But remember, I sampled this set randomly from my data set. And so you could hope, because it was a random sample, it should well represent the data. In particular, you could hope that most points are close to a sample point. And so that's going to be something we use crucially. So what we could hope for is for the points that weren't in the sample, but were close to some point in the sample, we can get a good approximation for those. So we could hope to extend the guarantee. We have a good guarantee for the points in the sample. We want to, like that's like say the point Z here, we want to extend the good approximation guarantee to a large neighborhood around that point. And that'll be our main goal. If we can do that, then we can get a good algorithm, at least for the close points. And so what's the kind of statement that I want to prove? I want to prove something that reads like this. If I have two sets A and B, two points in the EMD metric, these are sets of size S, I want to show that if they're close to the sample omega, then their earth mover distance in the tree should be a good approximation of their original earth mover distance. It should be a log S approximation. So I want to prove something like that. But the question is, first of all, what does it mean to be close to a sample? So I have two sets here. I could use the earth mover distance, but first note that like I don't need A and omega to like really have close earth mover distance. I don't need points in omega to be close to A. I just need every point in A sort of to be close to omega because I need it to not go far until it hits a point in omega. Omega can have many more points than A. So it turns out that I can use a much weaker notion of distance. And this is the so-called chamfer distance. So this is something that is actually, when I mentioned these applied papers earlier, they tend to use this distance because it's a little bit easier and it actually models this idea of containment. Is A contained in B? So what is the chamfer? It's you can think of it for the purposes of this talk is the cost of moving every point in A to its nearest point in omega. So it's just the sum over all the points in A, distance to the nearest point in omega, and then you sum that up. So it doesn't need to be a matching. 2 points in A can go to the same nearest point in omega. And in fact, some points in omega don't need to be matched at all. So it's a relaxation of earth over distance. So now that I have this definition, this is what I'm going to use to measure distance to my sample. And so now, sort of the main theorem of the main technical lemma of this work is what I'm going to call the strong chamfer extension lemma. It's called strong because there was a weak chamfer extension lemma, but I cut it from the slides, and so at some point I should remove the word strong. But this is ultimately what we prove in the paper. So what does it say? What is the main result here? It's that I want to bound the distance in the tree between the earth mover distance between A and B. And remember, we have some non-contracting statements, so we only want to upper bound it. So what we want to upper bound it by is log S times the original earth mover distance. So we'll have that, but now we're going to have an extra term, approximation term, which we're going to try to show is not too large. So what is this extra approximation term? Well, it's a function of how far away A is from the sample omega. So what it is this log of the chamfer distance from A to omega divided by the earth mover distance from A to B. So what is this saying? What this is saying is that if A is a point in earth mover distance, its extra approximation factor is log of the ratio of how far it is from the sample divided by how far it is from B. So if it's not too much further from the sample than it is from B, if it's only, let's say, polylog S further, then because this ratio is sitting in a log, I'll only get a log S flow up in the approximation. So the picture, like if I have A and B and their distance R, but R is much smaller than the distance to omega, but let's say the distance is only R times log 10S from the nearest sample point omega. Well, then this is saying that A and B will get a better approximation. It'll only be a log S blow up because this ratio is bounded by like log 10S. So just to summarize that, if the ratio, yeah.
I thought I understood the formula, but maybe the picture. What is the turquoise circle? Is just some ball around a sample point.
Yeah, this is just a metric ball.
This is how big a ball you need to include.
Yeah. I'm saying this is like the neighborhood, the chamfer neighborhood. These are individual points, not sets. So I've cheated a little bit here, but if the chamfer distance is just the actual distance if they're single individual points, right? So like for single points, this is saying that 2 points that are distance R, as long as their distance at most R times log 10S from a sample point, we'll get a good approximation.
But in the real thing you're saying, the radius has to be big enough to include all the points in A.
Yeah, but R is the threshold for the sum of the EMD. So you can think of R as being the EMD you care about. Yeah. And chamfer distance is always less than earth mover distance.
Yeah.
So you'll basically get things will be on the right scale. Like, so your points will be further away from the sample than they are to be on average, but they won't be that much further away. And if they are, we'll see how to deal with them. Like maybe a lot of them are far, and that's fine. We'll deal with them. We'll deal with them in another way.
Can you cope if 99% of the points are close to the sample? Does that even help you?
If 99% of the points are close to the sample, if they're close to the sample, that's good, right? If the points are close to the sample, then those points get the improved approximation.
If some of them are not,
yeah, that's fine. Yeah. I'll tell you what we do for the far points. Like the point being that the far points are the one line answer is the far points are so far that we can use a worse LSH to split them away.
Yeah.
And they're far points, so I don't want them to collide. So I could use a worse LSH to split them away, and they'll still have the property that the close points collide. I guess we started a little late, but I'll skip. There is this maybe isn't very insightful, but if you're interested in how we prove such a thing, I could tell you afterwards. But this is a very short description. So now let me just answer that question, say how we glue everything together. So what we're going to try to do now is handle two different cases. One, the case where the point set is close to a sample, and one where it's not. So you could think of this point as being the query. I want to figure out whether if it's close to a random sample, I can do one thing. If it's not, I'll have to do something else. And so I'm going to write this term. I'm going to call a point R locally dense if it satisfies this definition. If its chamfer distance from it to a randomly sampled point omega, subset omega, is at most R times log 10s. This is just a definition. You can interpret it as A is close to a random sample. And R is the scale for this hashing. So if this is the case, then we already just on the last slide informally proved this lemma 1, which says that if A is close, if it's locally dense, then you can use the sample tree embedding, then compose that with the L1 thing afterwards to get a good hash family. You can get an epsilon R C times R data dependent LSH, where C is log S log S. And this log S came from this chamfer ratio. The chamfer was log 10s. This was R. The chamfer was log 10s R. This was R. And so, okay, we get a good approximation in this case. What about if we're not locally dense? Well, then, what I want to claim is that this earlier hash function is enough. And the picture is that A is not close to a sample, but it's even it's really far from B. It's the distance you care about is R, and the chamfer distance is less than the earth mover distance. So if the chamfer distance from this thing is far, the earth mover distance from it is better be at least as far. The fact that this is true is very straightforward. There's that inequality. So A is and remember what does LSH guarantee? LSH says that close points should always collide with some good probability, and far points should not collide. But what is far? Far is defined as R times some approximation factor. But the earlier paper had a worse approximation factor. It was log squared S. But here far is really far. It's log 10s. So if I'm that far from my point, I could just use the earlier log squared S to split me from my points. But what's the key fact? Where am I using the fact that I'm having a weaker data dependent LSH? And that's that, just because I'm far from the random sample doesn't mean I'm at the point actually, not all the points need to be that far. But I only need, remember that this is exactly the definition of a data dependent LSH. I only need to separate from far points on average over a draw for my data set. And this omega was exactly drawn on average from the data set. So I get exactly the guarantee I was hoping to get. I only needed to split on these far points on average. And so that's why I don't actually get the stronger guarantee of splitting from R points. I only get it on average because omega was a sample. So that's intuitively how we handle the far points. And just we're basically done here. These are the two things we just said. The points that are close to our sample, the sample tree thing gives a good approximation. If they're far, then I can handle them with the worst approximation from earlier work. And in both cases, we get an approximate LSH. And then lastly, you need one hash function at the end of the day. And so when I have my query point, I need to decide, do I hash it with this or do I hash it with this? Because I need just a single hash function. And the sort of answer to that question is that there's actually a very simple way to test what case you're in. Because what you can do is when you're pre-processing the data set, you can hash all the points with this LSH. If you look at the hash function that your point is in, if there's a lot of points in there, then you can you have to prove this kind of thing, but you can prove a statement like saying if there's a lot of points in the hash bucket, then you have a lot of points nearby you. Therefore, you must be locally dense. And so therefore, you must be able to get a good approximation for sample tree. So algorithmically, you can actually check the condition of whether or not you're locally dense and use that to decide which one to use. And that's how we sort of finish the whole thing. So here was the picture again of what we did. We had these two tree embeddings. One was worse than the other, but one had approximation depending on the data set. So we sampled down the data set, and then sort of a lot of the key ideas were how do we extend the guarantee on the sample to the guarantee on the entire universe. And then we can't extend it to the entire universe, but we can extend the guarantee to a neighborhood of the sample. And for points not in the neighborhood, we split them with the earlier embedding. So yeah, thanks for sticking with me through that. Maybe before I end, I'll just say one quick thing about open problems. So some natural questions you can ask, like we've been working in this area of using LSH and techniques for high-dimensional geometry for about 4 or 5 years now. At least I've been working in that area with Eric on this. And there's a lot of we still have a lot of gaps between what we're able to do for EMD and what we could theoretically hope to do. So you could hope for a constant approximation for nearest neighbor search. We were actually able to show in this paper, we were able to rule out the possibility of getting localities of hash functions to give you a constant approximation for EMD. There was a caveat, we weren't able to rule them out if, for example, they had a very small probability of close points colliding. This is almost never the case, but mathematically you could have that, and so we don't rule this out fully. And LSH isn't maybe the only way to solve nearest neighbor search, but then again, we can't really prove runtime lower bounds, so this is maybe the best we could hope, some strong evidence that you can't get a constant approximation for nearest neighbor search. But we could hope to get a better approximation for sketching. So there's this model called sketching. This is the last thing I'll say. And this is a model that's also very important. And so the way this works is I'll have two parties, Alice and Bob. Alice is going to have the set A, Bob is going to have the set B, and their goal is to compute the Earth mover distance between A and B. But they want to do this by communicating very little. In fact, they don't want to send you could send the whole set, but they don't want to communicate the whole set. So instead of S bits, maybe they want log S bits, or even square root S bits. I don't know how to do that either. And the goal is what is the best approximation you can get. And note a very simple fact, if I had a data independent LSH for EMD, I can solve this problem. Because Alice and Bob, they can both hash their A and B using the LSH, and then they can just send in the name of the hash bucket and check whether it was the same or not. But note that this new result, you could hope that it gives you a better algorithm for this with log S approximation, but it's not clear how to do it because it's a data dependent hash function. So for Alice and Bob to actually compute the hash bucket or to compute the hash function, they need to know each other's input, which is sort of the whole point of the problem. So we had some new ideas here, but they're not actually enough yet to get the sketching problem. And so for sketching, still the best we know is a log squared S with there is a lower bound that's for some constant, but you could hope you did much better lower bound. For streaming algorithms, you can now get a log S approximation in 2 passes because it turns out this data dependent thing, you can estimate the weights on one pass and then estimate the cost on the second pass. But for one pass, we still don't know how to do it. And then now we can get a log S for nearest neighbor search. So we're working our way there, but there's still large gaps. But yeah, thank you so much for sticking with me.